Welcome back. Chapter 6, we're going to talk about R sub e, the exponential growth rate, and the doubling period. Sometimes we can look at a table and tell when a virus doubles in population. And of course, this formula gives you a very quick way to calculate R sub e. It's just natural log of 2 over the time to double. I could derive this if we had time, but you can probably look that up if you want. We have a situation here where t equals 0, we have 15 infections, t equals 1, 18, t equals 2, 22, all the way down to what's double 15 is 30. Well, when we get to t equals 4 days, we have 31 infections. It's more than doubled. What's the time to double? Well, we could use 4 as an estimate, or I suppose if you wanted, you could back it off to let's see, it took 1 whole day for 5 infections, so that's about a fifth of a day. So you could use somewhere in here is about t equals 3.8 days. That's a seat of the pants way of doing something called interpolation. You can set up a proportion or just wing it by inspection. That would be a little bit more precise. Of course, with this virus spread, this is sometimes pretty rough data anyway. So now we want to set up the model. What's I0? I0 is equal to 15. So we have I0 is 15, and then RE is going to be natural log of 2 divided by 3.8. Which is equal, let me grab my calculator. And we get about 0.182. If this is 2 sig figs, I'll use 2 sig figs here. So our model is simply I of t is equal to 15 e to the 0.18 t. Very simply put, we have that model with very little work. So that's about all we did in this chapter. So we have, this is, just to reiterate, this is a sequence of very short lessons. So we'll be back. Chapter 7, we're going to talk about basic reproduction numbers and also effective reproduction numbers. So that's pretty important. We'll work probably several videos on that chapter.